Okay, we're coming to the end of our brief digression on power functions, which of course ended up being anything but brief. We have what I'm going to call a capstone activity that I really do want you to do. And that capstone activity goes as follows. First thing you do is you make your own pendulum. I recommend getting something, you might not have washers around the house, but you might well, a ring. Now, if the ring has a heavy stone or something in it, you want that stone to be located halfway between the bottom and the top. In other words, the stone would be over here, right here, even with the middle, rather than at the bottom or the top, because you would want the center of mass of the pendulum to be pretty much in the center. But you could use a ring, you could use something similar. It doesn't even have to be something really small. It could be a fairly big circular object. Okay, anyhow, you make your own pendulum and use fine thread. Don't use a big thick rope with a little tiny ring. That rope is going to have mass. You want to use something that has very little mass compared to the pendulum. Excuse me, so a thin thread would be good. Okay, so make your own pendulum, then observe counts for several different lengths of a pendulum. You want a pretty wide variety of lengths. You get a better curve, a more reliable set of data if you use a pretty wide range of length. The greatest length might be 10 times the least. You can decide what it is that you think gives you the data that allows you to develop the best model, and you should think about that. Okay, you shouldn't just blindly follow instructions. Think about what you're doing. Think about how it fits in with everything that we're talking about here. Okay, then go ahead and make a graph of frequency versus length. Okay, if you're counting for a minute, then your frequency is cycles per minute. If you're counting for 100 seconds, well, frequency will be cycles per 100 seconds. Or if you want, you can divide the number of cycles by the number of seconds you observe and get the frequency in just cycles per second. That's your choice. Whatever you think is going to work best. I would use as default count per minute, number of counts per minute. Okay, having graphed the frequency versus length, and to graph that, you will have a scale. When you measure the pendulum, you're going to measure it in inches or centimeters or feet or miles or whatever you happen to have handy. If you have a mile stick, go ahead and measure it with that. Okay, so you're going to have a scale. Whatever scale is okay. Not everybody has to use the same scale, and as we'll see, it's easy to convert one scale to the other. Okay, so you get a scale, and you'll have a frequency scale. You know, as I said, it might be cycles per minute, it might be cycles per 100 seconds, it might be half cycles per minute. That would be a measure of frequency. As long as you're specific about what your measure of frequency is, that's okay. You could go cycles per second, whatever. As you see, once you have the scale, then your X and your Y are going to be in that scale, and when you use the X and the Y here to determine the value of A, then your model is going to come out consistent with your scale. Okay, now having made that graph, and make a careful graph, make a good graph, ignore your scale and sketch your trend curve. Okay, sketch a good curve that represents the trend of your data. And I said sketch, and it didn't really have the T in there, did I? Okay. Well, there it is, and it looks even worse than it did. Sketch the trend curve. Okay, then, totally ignore your data points. You're pretty much done with your data points. You've got your curve. Now remember, you sketch a smooth curve. You've seen me sketch smooth curves. We don't try to wiggle the curve around to go through data points. I think what I said previously is pretty clear on that. You want the trend, and the trend doesn't wiggle around to find points where you miscounted and so forth, or points where you just, you were between 62 and 63 cycles and it was 63, and it really probably was about 62 and a half. So you've got an error there. You don't wiggle around to get your data points. You don't wiggle around to get your curve. You try to get your data points to fit the curve. Okay, so we ignore the data points, and we use the curve to estimate the y factor. Okay, and we know what that means by now. Then we find the power p for our model, and that's just the log of the y factor over the log of 2. Now, if you came into the course with a background that included exponential and logarithmic functions in these calculations, you might well have proven why this is. There is a proof. It's not that difficult, but you've got to have the right background. So whether you have the background, and whether even if you had the background, you did that proof or not, you got this thing that you can treat right now as a formula, but understand that your knowledge won't be complete until you have that proof. And that might be off in the future for many of you who haven't even had the course where that would be, where you develop the tools you need to do this. Okay, so you find this log and you write your model y equals ax to the p, just as we did over here. Well, we were doing more than that here. You find your y factor and you write model y equals ax to the p, which would be like y equals ax to the 0.68. This is where you've found your y factor and used it to find your power, and that's what you're going to put in here. Then you pick any old point on the curve. Well, not any old point. You probably pick a point somewhere in the fat part of the curve, not too close to one end or the other, and find its x and y coordinates. And there might even be an advantage to getting one of your points further out here. Okay, a point on the curve, and find the x and the y coordinates of that point. You will have a scale, and now you can use the scale. Substitute, as we did here, and solve for a, and then write your model. Okay, well, here we substituted in our frequency and our length, solve for a, and then we wrote our model using that solution for a, substituting that for a in the model. And we get our model, and then I rewrote the model with f equals 4.9 L to the point, using f and L instead of y and x. Okay, so there's our model. And then there's one more step. For each measured length L, you want to use the model to find the frequency. Now, you observed a frequency for each of your measured lengths. Okay, and we're going to compare what the model says with what you observed. But we use the model to find f or to predict f. So that means we plug the length in, whatever your model is, whatever your power is, whatever your coefficient here is. You plug in the length and you do the calculation and you get a frequency. Ideally, that frequency matches the frequency you observed, but because there's uncertainty in your observations, it's not going to match completely. Okay, in the first place, this result will generally have an infinite number of significant figures. You might not have them all. You might not want to write them all down. Certainly you don't. There are an infinite number of them. But you certainly didn't observe your frequencies to a large number of significant figures. You probably just observed them to, at best, within a quarter of a count, more likely within half a count or within a count. And then maybe you didn't count correctly, because as I said, counting is a challenge for many people, for most people, counting accurately. So we do all that, and we have a good start on what I'm calling this capstone project. There's more, and I'll go on with this in the next video.